Advanced Audio Coding is an audio coding standard for lossy digital audio compression. Designed to be the successor of the MP3 format, AAC generally achieves better sound quality than MP3 at similar bit rates. AAC has been standardized by ISO and IEC, as part of the MPEG-2 and MPEG-4 specifications. Part of the AAC known as high-efficiency advanced audio coding, which is part of MPEG-4 audio, is also adopted into digital radio standards like DAB+ and digital radio Mondiale, as well as mobile television standards DVB-H and ATSC-M. AAC supports inclusion of 48 full-bandwidth audio channels in one stream plus 16 low-frequency effects channels, up to 16 coupling, or dialogue channels, and up to 16 data streams. The quality for stereo is satisfactory to modest requirements at 96 kbits in joint stereo mode. However, hi-fi transparency demands data rates of at least 128 kbits. The MPEG-2 audio tests showed that AAC meets the requirements referred to as transparent for the ITU at 128 kbits for stereo, and 320 kbits for 5.1 audio. AAC is the default or standard audio format for YouTube, iPhone, iPod, iPad, Nintendo DSi, Nintendo 3DS, iTunes, DivX Plus Web Player and PlayStation 3. It is supported on PlayStation Vita, Wii, Sony Walkman MP3 series and later, Sony Ericsson, Nokia, Android, BlackBerry, and WebOS-based mobile phones, with the use of a converter. AAC also continues to enjoy increasing adoption by manufacturers of in-car audio systems. History: AAC was developed with the cooperation and contributions of companies including AT&T Bell Laboratories, Fraunhofer IIS, Dolby Laboratories, Sony Corporation and Nokia. It was officially declared an international standard by the Moving Picture Experts Group in April 1997. It is specified both as Part 7 of the MPEG-2 standard, and Subpart 4 in Part 3 of the MPEG-4 standard. Standardization: in 1997, AAC was first introduced as MPEG-2 Part 7, formerly known as ISO IEC 13818-7 1997. This part of MPEG-2 was a new part, since MPEG-2 already included MPEG-2 Part 3, formerly known as ISO IEC 13818-3, MPEG-2BC. Therefore, MPEG-2 Part 7 is also known as MPEG-2NBC, because it is not compatible with the MPEG-1 audio formats. MPEG-2 Part 7 defined three profiles: low complexity profile, main profile and scalable sampling rate profile. AAC-LC profile consists of a base format very much like AT&T's perceptual audio coding format, with the addition of temporal noise shaping, the Dolby Kaiser window, a non-uniform quantizer, and a reworking of the bitstream format to handle up to 16 stereo channels, 16 mono channels, 16 low-frequency effect channels and 16 commentary channels in one bitstream. The main profile adds a set of recursive predictors that are calculated on each tap of the filter bank. The successor uses a 4-band PQMF filter bank, with 4 shorter filter banks following, in order to allow for scalable sampling rates. In 1999, MPEG-2 Part 7 was updated and included in the MPEG-4 family of standard and became known as MPEG-4 Part 3, MPEG-4 Audio or ISO IEC 14496-3 1999. This update included several improvements. One of these improvements was the addition of audio object types which are used to allow interoperability with a diverse range of other audio formats such as Twin VQ, CELP, HVXC, text-to-speech interface and MPEG-4 structured audio. Another notable addition in this version of the AAC standard is perceptual noise substitution. In that regard, the AAC profiles are combined with perceptual noise substitution and are defined in the MPEG-4 audio standard as audio object types. MPEG-4 audio object types are combined in 4 MPEG-4 audio profiles: main, Scalable, speech and low-rate synthesis. The reference software for MPEG-4 Part 3 is specified in MPEG-4 Part 5 and the conformance bit streams are specified in MPEG-4 Part 4. MPEG-4 audio remains backward compatible with MPEG-2 Part 7. The MPEG-4 audio version 2 defined new audio object types, the low delay AAC object type, bit-sliced arithmetic coding object type, parametric audio coding using harmonic and individual line plus noise and error resilient versions of object types. It also defined 4 new audio profiles: high-quality audio profile, low-delay audio profile, natural audio profile and mobile audio internetworking profile. The HE-AAC profile and AAC profile were first standardized in ISO IEC 14496-3 2001/1 The HE-AAC v2 profile was first specified in ISO IEC 14496-3 2005/2 2006. The parametric stereo audio object type used in HE-AAC v2 was first defined in ISO IEC 14496-3 2001/2 2004. The current version of the AAC standard is defined in ISO IEC 14496-3 2009. AAC plus v2 is also standardized by ETS-IS TS 100 2005. The MPEG-4 Part 3 standard also contains other ways of compressing sound. These include lossless compression formats, synthetic audio and low bit rate compression formats generally used for speech. AAC's improvements over MP3, advanced audio coding is designed to be the successor of the MPEG-1 audio layer 3, known as MP3 format, which was specified by ISO IEC in 11172-3 and 13818-3. Blind tests in the late 1990s showed that AAC demonstrated greater sound quality and transparency than MP3 for files coded at the same bit rate, but since that time numerous codec listening tests have shown that the best encoders in each format are often of similar quality and that the quality is often dependent on the encoder used even within the same format. As an approximation, when using the best encoders, AAC's advantage over MP3 tends to be evident below around 100 kbits, but certain AAC encoders are not as good as the best MP3 encoder as they do not take optimal advantage of the additional encoding tools that AAC makes available. Improvements include more sample frequencies than MP3, up to 48 channels, arbitrary bit rates and variable frame length. Standardized constant bit rate with bit reservoir. Higher efficiency and simpler filter bank, higher coding efficiency for stationary signals, higher coding accuracy for transient signals, can use Kaiser-Bessel-derived window function to eliminate spectral leakage at the expense of widening the main lobe, much better handling of audio frequencies above 16 kHz, more flexible joint stereo, adds additional modules to increase compression efficiency, TNS, backwards prediction, PNS etc. These modules can be combined to constitute different encoding profiles. Overall, the AAC format allows developers more flexibility to design codecs than MP3 does, and corrects many of the design choices made in the original MPEG-1 audio specification. This increased flexibility often leads to more concurrent encoding strategies and, as a result, to more efficient compression. However, in terms of whether AAC is better than MP3, the advantages of AAC are not entirely decisive, and the MP3 specification, although antiquated, has proven surprisingly robust in spite of considerable flaws. AAC and HE-AAC are better than MP3 at low bit rates. This is especially true at very low bit rates where the superior stereo coding, pure MDCT, and better transform window sizes leave MP3 unable to compete. While the MP3 format has near universal hardware and software support, primarily due to MP3 being the format of choice during the crucial first few years of widespread music file sharing distribution over the Internet, AAC is a strong contender due to some unwavering industry support. How AAC works. AAC is a wideband audio coding algorithm that exploits two primary coding strategies to dramatically reduce the amount of data needed to represent high-quality digital audio. Signal components that are perceptually irrelevant are discarded. Redundancies in the coded audio signal are eliminated. The actual encoding process consists of the following steps. The signal is converted from time domain to frequency domain using Ford-modified discrete cosine transform. This is done by using filter banks that take an appropriate number of time samples and convert them to frequency samples. The frequency domain signal is quantized based on a psychoacoustic model and encoded. Internal error correction codes are added. The signal is stored or transmitted. In order to prevent corrupt samples, a modern implementation of the LUN-MOD-N algorithm is applied to each frame. The MPEG-4 audio standard does not define a single or small set of highly efficient compression schemes but rather a complex toolbox to perform a wide range of operations from low bitrate speech coding to high-quality audio coding and music synthesis. The MPEG-4 audio coding algorithm family spans the range from low bitrate speech encoding to high-quality audio coding. AAC offers sampling frequencies between 8 kHz and 96 kHz and any number of channels between 1 and 48. In contrast to MP3's hybrid filter bank, AAC uses the modified discrete cosine transform together with the increased window lengths of 1024 or 960 points. AAC encoders can switch dynamically between a single MDCT block of length 1024 points or 8 blocks of 128 points. If a signal change or a transient occurs, 8 shorter windows of 128 1/20th points each are chosen for their better temporal resolution. By default, the longer 1024 point/960 point window is otherwise used because the increased frequency resolution allows for a more sophisticated psychoacoustic model, resulting in improved coding efficiency. Modular encoding, AAC takes a modular approach to encoding. Depending on the complexity of the bitstream to be encoded, the desired performance and the acceptable output, implementers may create profiles to define which of a specific set of tools they want to use for a particular application. The MPEG-2 Part 7 standard was first published in 1997 and offers 3 default profiles: low complexity the simplest and most widely used and supported. Main profile like the LC profile, with the addition of backwards prediction. Scalable sample rate aka sample rate scalable. The MPEG-4 Part 3 standard defined various new compression tools and their usage in brand new profiles. AAC is not used in some of the MPEG-4 audio profiles. The MPEG-2 Part 7 AAC-LC profile, AAC main profile and AAC-SSR profile are combined with perceptual noise substitution and defined in the MPEG-4 audio standard as audio object types. These are combined with other object types in MPEG-4 audio profiles. Here is a list of some audio profiles defined in the MPEG-4 standard. Main audio profile defined in 1999, uses most of the MPEG-4 audio object types. Scalable audio profile defined in 1999, uses AAC-LC, AAC-LTP, AAC Scalable, Twin VQ, CELP, HVXC, TTSI, speech audio profile defined in 1999, uses CELP, HVXC, TTSI, synthetic audio profile defined in 1999, TTSI, main synthesis, high-quality audio profile defined in 2000, uses AAC-LC, AAC-LTP, AAC Scalable, CELP, AAC-LC, AAC-LTP, AAC Scalable, EOCELP, Low Delay audio profile. Defined in 2000, uses CELP, HVXC, TTSI, AAC-LD, ASELP, HVXC, Mobile Audio Internetworking profile defined in 2000, uses ERAAC-LC, AAC Scalable, Twin VQ, ERBSAC, AAC-LD, AAC profile defined in 2003, uses AAC-LC, High-efficiency AAC profiler Euro-defined in 2003, uses AAC-LC, SBR. High-efficiency AAC V2 profiler Euro-defined in 2006, uses AAC-LC, SBR, PS. One of many improvements in MPEG-4 audio is the object type, long-term prediction, which is an improvement of the main profile using a forward predictor with lower computational complexity. AAC Error Protection Toolkit. Applying error protection enables error correction up to a certain extent. Error-correcting codes are usually applied equally to the whole payload. However, since different parts of an AAC payload show different sensitivity to transmission errors, this would not be a very efficient approach. The AAC payload can be subdivided into parts with different error sensitivities. Independent error-correcting codes can be applied to any of these parts using the error protection tool defined in MPEG-4 audio standard. This toolkit provides the error-correcting capability to the most sensitive parts of the payload in order to keep the additional overhead low. The toolkit is backwardly compatible with simpler and pre-existing AAC decoders. A great deal of the toolkit's error correction functions are based around spreading information about the audio signal more evenly in the data stream. Error-resilient AAC. Error resilience techniques can be used to make the coding scheme itself more robust against errors. For AAC, 3 custom-tailored methods were developed and defined in MPEG-4 audio: Huffman code word reordering to avoid error propagation within spectral data, virtual codebooks to detect serious errors within spectral data, reversible variable length code to reduce error propagation within scale factor data. Aac Low Delay. The MPEG-4 Low Delay audio coder is designed to combine the advantages of perceptual audio coding with the low delay necessary for two-way communication. It is closely derived from the MPEG-2 advanced audio coding format. Licensing and patents. No licenses or payments are required to be able to stream or distribute content in AAC format. This reason alone can make AAC a much more attractive format to distribute content than its predecessor MP3, particularly for streaming content depending on the use case. However, a patent license is required for all manufacturers or developers of AAC codecs. For this reason, free and open-source software implementations such as FFmpeg and HE-AAC may be distributed in source form only, in order to avoid patent infringement. Extensions and improvements. Some extensions have been added to the first AAC standard, perceptual noise substitution, added in MPEG-4 in 1999. It allows the coding of noise as pseudo-random data. Long-term predictor, added in MPEG-4 in 1999. It is a forward predictor with lower computational complexity. Error resilience, added in MPEG-4 audio version 2 in 2000, used for transport over error-prone channels. AAC-LD, defined in 2000, used for real-time conversation applications. High-efficiency AAC, aka AAC plus V1 or AAC plus, the combination of SBR and AAC-LC. Used for low bit rates. Defined in 2003. HE-AAC V2, aka AAC plus V2 or HE-AAC plus, the combination of parametric stereo and HE-AAC. Used for even lower bit rates. Defined in 2004 and 2006. MPEG-4 scalable to lossless, defined in 2006, can supplement an AAC stream to provide a lossless decoding option, such as in Fraunhofer IIS's HE-AAC product. Container formats. In addition to the MP4, 3GP and other ISO-based media file format-based container formats for file storage, AAC audio data was first packaged in file-based form for the MPEG-2 standard by using a more basic format called Audio Data Interchange format, consisting of a single header followed by the raw AAC audio data blocks. However, if the data is to be streamed within an MPEG-2 transport stream, a self-synchronizing format called an audio data transport stream is used, consisting of a series of frames, each frame having a header followed by the AAC audio data. This file and streaming-based format are defined in MPEG-2 Part 7, but are only considered informative by MPEG-4, so an MPEG-4 decoder does not need to support either format. These containers, as well as a raw AAC stream, may bear the Aac file extension. MPEG-4 Part 3 also defines its own self-synchronizing format called a low-overhead audio stream that encapsulates not only AAC, but any MPEG-4 audio compression schemes such as Twin VQ and ALS. This format is what was defined for use in DVB transport streams when encoders use either SBA or parametric stereo AAC extensions. However, it is restricted to only a single non-multiplexed AAC stream. This format is also referred to as a low-overhead audio transport multiplex, which just an interleaved multiple-stream version of LOAS. Products that support AAC, HDTV standards, Japanese ISDBT. In December 2003, Japan started broadcasting terrestrial DTV ISDBT standard that implements MPEG-2 video and MPEG-2 AAC audio. In April 2006, Japan started broadcasting the ISDBT mobile subprogram, called 1seg, that was the first implementation of video H-264/AVC with audio HE-AAC in terrestrial HDTV broadcasting service on the planet. International ISDBT-B. In December 2007, Brazil started broadcasting terrestrial DTV standard called International ISDBT-B that implements video coding H-264/AVC with audio AAC-LC on main program and video H-264/AVC with audio HE-AAC-V2 in the 1seg mobile subprogram. DVB, the ETSI, the standards governing body for the DVB suite, supports AAC, HE-AAC and HE-AAC-V2 audio coding and DVB applications since at least 2004. DVB broadcasts which use the H-264 compression for video normally use HE-AAC for audio. Hardware, iTunes and Ipod. In April 2003, Apple brought mainstream attention to AAC by announcing that its iTunes and Ipod products would support songs in MPEG-4 AAC format. Customers could download music in a closed-source digital rights management restricted form of AAC via the iTunes Store or create files without DRM from their own CDs using iTunes. In later years, Apple began offering music videos and movies, which also use AAC for audio encoding. On May 29, 2007, Apple began selling songs and music videos free of DRM from participating record labels. These files mostly adhere to the AAC standard and are playable on many non-Apple products, but they do include custom iTunes information such as album artwork and a purchase receipt, so as to identify the customer in case the file is leaked out onto peer-to-peer networks. It is possible, however, to remove these custom tags to restore interoperability with players that conform strictly to the AAC specification. As of January 6, 2009, nearly all music on the USA region iTunes Store became DRM-free, with the remainder becoming DRM-free by the end of March 2009. iTunes supports a variable bit rate encoding option which encodes AAC tracks in an average bit rate scheme. As of September 2009, Apple has added support for HE-AAC only for radio streams, not file playback, and iTunes still lacks support for true VBR encoding. The underlying QuickTime API does offer a true VBR encoding profile, however. Other portable players, Archos, Kowon, Creative Zen Portable, Microsoft Zune, Samsung Yep, SanDisk Sansa, Sony PlayStation Portable with firmware 2.0 or greater, Sony Walkman, Nintendo DSi, Nintendo 3DS, any portable player that fully supports the Rockbox third-party firmware, mobile phones. For a number of years, many mobile phones from manufacturers such as Nokia, Motorola, Samsung, Sony Ericsson, BenQ Siemens and Philips have supported AAC playback. The first such phone was the Nokia 5510 released in 2002, which also plays MP3s. However, This phone was a commercial failure, and such phones with integrated music players did not gain mainstream popularity until 2005, when the trend of having AAC as well as MP3 support continued. Most new smartphones and music-themed phones support playback of these formats. Sony Ericsson phones support various AAC formats in MP4 container. AAC-LC is supported in all phones beginning with K700. Phones beginning with W550 have support of HE-AAC. The latest devices such as the P990, K610, W890i and later support HE-AAC v2. Nokia XPRESS Music and other new generation Nokia multimedia phones like N and E series also support AAC format in LC, HE, M4A and HEV2 profiles. BlackBerry, RIM's latest series of smartphones such as the 8100, 9500 and 8800 support AAC. BARDA-OS, Apple's iPhone supports AAC and Fairplay protected AAC files formerly used as the default encoding format in the iTunes Store until the removal of DRM restrictions in March 2009. All recent Android phones support AAC-LC, HE-AAC and HE-AAC v2 and MP4 or M4A containers along with several other audio formats. From Android 3.1 also raw ADTS files are supported. Android 4.0 can also encode these kind of files. WebOS by HP Palm supports AAC, AAC+, EAAC+, and M4A containers in its native music player as well as several third-party players. However, it does not support Apple's Fairplay DRM files downloaded from iTunes. Windows Phone Silverlight Runtime supports AAC-LC, HE-AAC and HE-AAC v2 decoding. Other devices, Apple's Ipod, supports AAC and Fairplay protected AAC files used as the default encoding format in the iTunes Store. Palm OS PDAs, many Palm OS-based PDAs and smartphones can play AAC and HE-AAC with the third-party software Pocket Tunes. Version 4.0, released in December 2006, added support for native AAC and HE-AAC files. The AAC codec for TCP/MP, a popular video player, was withdrawn after version 0.66 due to patent issues, but can still be downloaded from sites other than corecodec.org. Core Player, the commercial follow-on to TCP/MP, includes AAC support. Other Palm OS programs supporting AAC include Canoma Player and Aero Player. Microsoft Windows mobile platforms support AAC either by the native Windows Media Player or by third-party products. Epson supports AAC playback in the P2000 and P4000 multimedia photo storage viewers. This support is not available with their older models, however. The Sony Reader portable ebook plays M4A files containing AAC, and displays metadata created by iTunes. Other Sony products, including the A and E series network Walkmans, support AAC with firmware updates while the S series supports it out of the box. Nearly every major car stereo manufacturer offers models that will play back M4A files recorded onto CD in a data format. This includes Pioneer, Sony, Alpine, Kenwood, Clarion, Panasonic, and JVC. The Sonos digital media player supports playback of AAC files. The Barnes & Noble Nook Color electronic book reader supports playback of AAC encoded files. The Rocker Sound Bridge network audio player supports playback of AAC encoded files. The Squeezebox network audio player supports playback of AAC files. The PlayStation 3 supports encoding and decoding of AAC files. The Xbox 360 supports streaming of AAC through the Zune software, and if supported iPods connected through the USB port. The Wii video game console supports AAC files through version 1.1 of the photo channel as of December 11, 2007. All AAC profiles and bit rates are supported as long as it is in the M4A file extension. This update removed MP3 compatibility, but users who have installed this may freely downgrade to the old version if they wish. The LiveScribe Pulse and Echo smartphones record and store audio in AAC format. The audio files can be replayed using the pen's integrated speaker, attached headphones, or on a computer using the LiveScribe desktop software. The AAC files are stored in the user's My Documents folder of the Windows OS and can be distributed and played without specialized hardware or software from LiveScribe. Software: almost all current computer media players include built-in decoders for AAC, or can utilize a library to decode it. On Microsoft Windows, DirectShow can be used this way with the corresponding filters to enable AAC playback in any DirectShow-based player. Mac OS X supports AAC via the QuickTime libraries. Adobe Flash Player, since version 9 Update 3, can also play back AAC streams. Since Flash Player is also a browser plugin, it can play AAC files through a browser as well. The Rockbox open source firmware also offers support for AAC to varying degrees, depending on the model of player and the AAC profile. Optional Ipod support for the XBOX 360 is available as a free download from XBOX Live. Following, a non-comprehensive list of other software player applications, 3IVX MPEG-4, a suite of DirectShow and QuickTime plugins which support AAC encoding or AAC/HE-AAC decoding in any DirectShow application. Core Player also supports LC and HE-AAC. Easy CD DAW Extractor for Windows, CD Ripper and Audio Converter, which includes an AAC encoder that supports LC and HE-AAC. FFDSHOW is a free open-source DirectShow filter for Microsoft Windows operating systems that uses FAAD2 to support AAC decoding. FABA 2000 is a freeware audio player for Windows that supports LC and HE-AAC. JAAD is an open-source decoder written in Java. K Multimedia Player also supports AAC. KSP Sound Player also supports AAC. MediaMonkey, AIMP, Media Player Classic Home Cinema, and Player Auxine are often used as AAC decoders on Linux or Macintosh. Music B, an advanced music manager/player that also supports encoding/ripping. Real Player includes Real Networks Real Audio 10 AAC encoder. Songbird for Windows, Linux and Mac OS X supports AAC, including the DRM rights management encoding used for purchased music from the iTunes Store, with a plug-in. Sony Sonic Stage also support AAC. VLC Media Player supports playback and encoding of MP4 and AAC files. Winamp for Windows, which includes an AAC encoder that supports LC and HE-AAC. Windows Media Player 12, released with Windows 7, supports playback of AAC files natively. Another Real product, Rhapsody supports the Real Audio AAC codec, in addition to offering subscription tracks encoded with AAC. XBMC supports AAC. XMMS supports MP4 playback using a plugin provided by the FAR2 library. Some of these players also support the decoding of ADTS using the Shoutcast protocol. Plugins for Winamp and FABA 2000 enable the creation of such streams. Nero Digital Audio, in May 2006, Nero AG released an AAC encoding tool free of charge, Nero Digital Audio, which is capable of encoding LC-AAC, E-AAC and HE-AAC v2 streams. The tool is a command line interface tool only. A separate utility is also included to decode to PCMWAV. Various tools including the FABA 2000 audio player, media coder, MIGWI encoding frontend and dPowerAmp can provide a GUI for this encoder. FAAC and FAAD2. FAAC and FAAD2 stand for Freeware Advanced Audio Coder and Decoder 2 respectively. FAAC supports audio object types LC, main and LTP. FAAD2 supports audio object types LC, main, LTP, SBR and PS. Although FAAD2 is free software, FAAC is not free software. FFmpeg, FFmpeg's LibAvodec library contains free software codecs for both encoding and decoding AAC. See also here for a list of other encoder-decoder libraries available. See also, comparison of audio coding formats, AAC-LD, MPEG-4 Part 14, AAC Apple's own lossless codec, 4Bs the main open, royalty-free competitor to AAC and MP3, Opus an open, royalty-free codec for both pre-encoded and interactive use, standardized in 2012. References. External links. Fraunhofer Audio Codecs, audiocoding.com home of FAAC and FAAD2, official MPEG website, AAC improvements and extensions, RFC 3016, RTP payload format for MPEG-4 audio-visual streams, RFC 3640, RTP payload format for transport of MPEG-4 elementary streams, RFC 4281, the codecs parameter for bucket media types, RFC 4337, MIME type registration for MPEG-4.